Hello. So here we are for weather to atmosphere in the vertical. Let's get that out of there this time. So we'll make this should be short. When you go to the OneNote, here's where it'll be. Right there, atmosphere in the vertical. And there's page 1, page 2, and page 3. Page 3 is the STUVI, what it's called, the diagram, where you're actually going to be graphing on there. When you open them, then it looks like this. So there's page 1. So all you're going to do here is this. Two of these right now are little Canadian activities. Pretty straightforward. Just read the directions here. So after completing this activity, you should be able to do these two things. Introduction just reminds you about troposphere and stuff like that. Essentially, we're going to have something called the standard atmosphere, which is the average basic atmosphere. You're going to graph one of those, and then you're going to graph a sounding from Buffalo. So you'll have one line on the graph that will be the average, and then another line that'll be from an actual day from Buffalo. Okay, so you just go right through these, right in order, just 1, 2, 3, 4, 5, and the next page, and questions as they come up. So I've got this little note on here. We mostly talk about millibars here. The United States, well, actually, was that in that other video? That should have been. So if you're watching the weather, which is a good idea, it'll make this all make more sense. When we're talking about air pressure, I guess that'll come up more soon. Millibar is sort of what the world uses. We still use inches of mercury here. In the United States, we're way behind, obviously, with that. So everybody else has gone to the metric system, and then really moved on to the hectopascal even. So these are equal to each other. So anytime you see anything on here that says hectopascal, millibar can be replaced there. Okay, so this page, and then there's a second page with some more data to plot on it. So you will go through answer number 1, and number 2, and then you'll plot these 3 points on the graph that we're going to look at here in a second. Then answer number 3, 4, and 5 based on those. 6 based on your little graph score. And then when you get to number 8, you're plotting whatever these are, 8 or 9, 7 or 8 points. Okay, so this is the Buffalo sounding. So this will be the actual one. So this you use with a dashed line, I think it tells you to use. So you'll have one dashed straight line, and the other one will be a solid line, okay, that you're plotting. And so this is the STUVI, it's called, vertical atmospheric chart that you're plotting on. So let's just talk about this for a second. Temperature across the bottom, getting warmer going to the right, colder going to the left. The bottom represents the ground, the surface of the earth. Over here we've got air pressure in hectopascals. You can scratch that out, but millibars if you want. Numbers are the same. And then over here is altitude. So if you notice some crazy things about this graph, one is that the lines are squished closer together. And that's because air pressure, if we remember, it's just a function of the amount of air above you. So as you go up, there's less and less air above you. So it's really squeezed down at the surface where gravity's pulling it tight. So as you get closer to the surface, there's more atmospheric pressure. That's where the most of it is. So 1013 is the average at the surface. And as you go up, it gets less and it spreads out. It gets less and less dense. Way up there, way up off the chart, somewhere would be 0, where we slide into space. And then over here is altitude going up, okay? Oh, that's also the reason why these numbers are backwards, right? As you go up, there's less millibars of air pressure. So there's more at the bottom. Okay, so they're backwards and then squeezed together. And then this is just altitude over here going up 2, 4, 6, 8, 10 in kilometers. So you're going to be plotting on there. You're going to have 2 lines and then answer some questions. So here's where you should pause the video, probably do the little activity, come back, and then we'll go over the answers because that's what we would do in class before we moved on. You will be submitting this one way or another. I'll figure out exactly how. So this little note that you can read just says it's probably a good idea to do this, not just circle the answers and submit it. You'll get some points for that, but ultimately at some point we're going to have to do a quiz or something, maybe a little Zoom synchronous kind of thing where we're all taking the quiz at the same time. Not sure yet, but that'll have to happen. So activity, come right back. Okay, welcome back. So your graph should kind of look like that. So here's the solid standard atmosphere line, the average, right? Notice right there, the top of the troposphere, the tropopause is about 11 kilometers, like we said earlier. Changes seasonally. And so on this day in Buffalo, this was the reading for the temperature, altitude, and air pressure. Okay. So there's certain ones we really want to spend some time talking on, but some of them you should just have figured out probably. So we'll just quickly give the answers here to say number 1. The little spaces that you filled in are 40, 100, and 16. Number 2, then you plotted the standard atmosphere. Number 3, we would say troposphere, then stratosphere. Number 4 is a good one. So when you did the, it asked you to get the rate of tropospheric temperature decrease with altitude in the standard atmosphere. So that's just this solid line. So how much on average is it dropping as you go up in degrees Celsius per kilometer? So it's just the distance from here to there in degrees divided by the change in altitude in kilometers. So you end up with 71.5 change there, total absolute degree change divided by 11 kilometers. And then your answer is 6.5 degrees Celsius per kilometer. So that means if you were in a weather balloon going up and you held the thermometer out, for every kilometer you went up, the temperature would drop 6.5 degrees Celsius. Okay. Number 5, answers are then 2 and 5. Number 6 is 6. 7 is 6 and 16. So basically what you're understanding here is the vast majority of the atmosphere is squeezed down very close to the surface of the Earth, right? If we look at half of the atmosphere, which is about 500 millibars, it's at about 6 kilometers, right? It goes up hundreds of kilometers, and half of the atmosphere by mass is squeezed into the bottom 6, which is very dense down here. Lots of air down there, okay? And then you plotted this buffalo sounding. Now here's where we want to talk about things. Number 9. The time of the observation, the troposphere over Buffalo was generally colder, definitely colder because it's to the left. This is the colder side. So on this day, the sounding was colder than average. Number 10, at Buffalo is located about 300 hectopascal right there, the top. Vertical thickness of the troposphere at Buffalo is less than the thickness of the standard, right? So it's thinner here, thicker here. This is the thickness from the surface to there. It's thinner here in Buffalo, right? So this illustrates the general relationship between average tropospheric temperature and the vertical extent of the troposphere. That is, the colder the troposphere, the thinner it is, right? So this one's colder and thinner, warmer and thicker. This relationship means that on average, on a global scale, the thickness of the troposphere decreases as latitude increases. So as you go from the equator to the pole, it's going to get thinner, right? If we had a little highly exaggerated drawing, Laundry's done. Let me just draw a picture in here. I don't have a whiteboard yet. I will here at some point, hopefully. Can you see that right there? So, wrong side. Here's our Earth inside there. I'll get a better picture of this to you somehow. So the atmosphere would be thinner at the poles, thicker at the equator. So that's very exaggerated drawing, but that's what it would. That's what we're saying. So as the atmosphere gets colder at the poles, the atmosphere gets thinner. So if we want to make another drawing, let's see if I can do a better one here with. So it's the same kind of idea. There's you standing at the equator, nice thick atmosphere, and then here's you standing at the poles, at the pole, thin. So the atmosphere wants to balance out. So what ends up happening then, in that case, we could say above you there's a lot of air, so it's high pressure at the equator, low pressure at the poles, right? That makes sense. And so then the atmosphere always wants to balance out so that air will move or flow from high to low always to flatten out, or try to, and that's what we call wind. So that's our next topic is high and low pressures, and the atmosphere balancing out in the form of wind. All right, so make sure you got that all completed. I'll get back to you at how we're going to submit that, maybe just in the OneNote. If you have any questions, send them.